Imagine trying to swim through honey. That is the reality for microscopic organisms, where the fluid viscosity completely overwhelms inertia. At this scale, the Reynolds number is typically less than 1,000th. If a swimmer simply opens and closes a single paddle, like a scallop, it will move forward during the opening stroke, but the closing stroke will perfectly reverse the flow field, pulling the swimmer back to its exact starting position. This time reversibility of the governing physics means that any simple symmetric motion produces zero net displacement. This fundamental constraint dictates the required complexity for all successful micro-robots and biological swimmers. The Reynolds number quantifies the ratio of inertial forces to viscous forces within a fluid. When this number is significantly less than 1, the flow is dominated entirely by viscosity, entering the regime known as Stokes flow. In this regime, the acceleration terms in the Navier-Stokes equations become negligible, simplifying the governing physics to the linear, time-independent Stokes equations. Crucially, the fluid velocity at any point is instantaneously proportional to the forces applied by the moving body boundaries. There is no momentum or memory stored in the fluid, meaning the flow field immediately adjusts to the boundary conditions. The Scallop Theorem, formulated by Edward Purcell, is a direct consequence of the linearity and time reversibility inherent in the Stokes equations. The theorem states that any swimming mechanism relying on a sequence of identical reciprocal shape changes cannot achieve net locomotion. Reciprocal motion means that the sequence of shape changes performed to move forward can be perfectly reversed in time, returning the body to its initial configuration through the exact same intermediate shapes. Since the fluid dynamics are linear, reversing the boundary motion simply reverses the resulting fluid velocity field, leading to zero net displacement over a full cycle.
To understand reciprocity, we map the swimmer's configuration onto a geometric shape space. A reciprocal stroke is one where the path taken in this shape space during the power stroke is identical to the path taken during the recovery stroke, only traversed in the opposite direction. For a single-hinged scallop, its configuration is defined by one angle. Opening the hinge corresponds to moving along a line segment in shape space, and closing it corresponds to moving back along the exact same line segment. The net displacement is the integral of the instantaneous velocity over the cycle, which must be zero due to the time reversibility of the fluid dynamics. To circumvent the Scallop theorem, a swimmer must employ a non-reciprocal gait. This means the path taken in the configuration space during the forward stroke must differ from the path taken during the recovery stroke. The swimmer must execute a cycle that encloses a non-zero area in its shape space. This enclosed area represents the asymmetry required to rectify the viscous forces and produce net motion. The complexity of the swimmer must be sufficient to allow for at least 2 independent degrees of freedom, enabling the creation of a closed-loop trajectory in the two-dimensional shape space. The simplest mechanism capable of non-reciprocal motion is Purcell's 3-link swimmer, often called the 3-hinge swimmer. This device consists of 3 rigid segments connected by 2 active hinges. By cyclically changing the angles of the 2 hinges independently, the swimmer gains the necessary 2 degrees of freedom. This allows the swimmer to execute a sequence of 4 distinct non-reciprocal strokes. This asymmetry in the motion cycle breaks the time reversibility constraint, enabling the swimmer to achieve net propulsion against the dominant viscous drag.
The 3-link swimmer operates by performing a sequence of 4 steps. First, changing the angle of the front hinge while keeping the rear hinge fixed. Second, changing the angle of the rear hinge while keeping the front hinge fixed. Third, reversing the front hinge angle. And finally, reversing the rear hinge angle. Because the drag forces depend non-linearly on the instantaneous shape of the body, the displacement achieved during the first 2 steps is not perfectly cancelled by the displacement during the reverse steps. The net result is a small forward displacement per cycle, proportional to the area enclosed in the two-dimensional shape space. In micro-robotics, implementing non-reciprocal motion often relies on external fields rather than internal motors. Magnetic actuation is a common method, where flexible chains of magnetic particles are manipulated by oscillating or rotating external magnetic fields. These fields induce non-reciprocal deformations, such as helical waves or propagating planar waves along the body. These induced waves effectively mimic the complex non-reciprocal motion required by the Scallop theorem, allowing artificial microswimmers to navigate highly viscous environments for tasks like targeted sensing or manipulation. The efficiency of a low Reynolds number swimmer is measured by the ratio of the energy expended to the distance traveled, often termed the swimming efficiency. This efficiency is inherently low because energy is continuously dissipated against viscous drag. Optimal gaits are those that maximize the enclosed area in shape space relative to the total path length traveled. Research focuses on optimizing the sequence and magnitude of hinge angle changes to maximize the net displacement per cycle while minimizing the required input power, typically resulting in complex, non-intuitive motion patterns.
The ability to design and control microswimmers that obey the Scallop Theorem is critical for biomedical applications. Micro-robots capable of navigating the human circulatory system, where the local Reynolds number is extremely low, can be used for targeted drug delivery. By precisely controlling the non-reciprocal actuation, these devices can deliver therapeutic agents directly to diseased tissues, minimizing systemic side effects. Further advancements focus on integrating sensing capabilities and biodegradable materials to create autonomous, functional micromachines for in vivo diagnostics and therapy.